Okay, on chapter 3, we're determining change, the derivatives. And this is section 3.2, where we're looking at exponential, logarithmic, and cyclic rate of change formulas. So the general rules for writing rate of change functions of exponential, logarithmic, and cyclic functions are going to be given in this section, and they're just going to be given like, this is the rule and how it works, except for when we get to the cyclic, and we'll do a little bit more with that one. So here are the rates of change of exponential functions. We have the e to the x derivative rule. And with that one, we have f of x is just equal e to x. And then the derivative of that is equal to e to the x as well. So both the original f of x is equal to e to the x and the derivative f of x or f prime of x is equal to e to the x. They're the same. So that's one case where we end up with something that is exactly the same, and that's with our exponential function. Now, we also have other types of exponentials, so it doesn't always apply. So what we have to do is use a general rule for exponentials. And so with that one, if we have f of x is equal to b to the x, so any, real number b has to be greater than 0, where here we had e, so, that's the difference. And then our f prime of x is equal to, and what we're going to do is we're going to take ln of b, and so that goes out in front, and then times b to the x. Now, if you think about that, if b was e, then we'd have ln of e, which is just 1, and then we'd still have e to the x. And so we could get that one from this one by just replacing the b with e, and we get back to our e to the x derivative rule, okay? We also have the natural logarithm. So with this one, so if our f of x is equal to ln of x, and again, x here has to be greater than 0 because we can't have negatives and take the log of them, then f prime of x is just simply 1 over x. And so you start with this, and your derivative is 1 over x. Now here we have the cyclic. So this is the kind of the more compound ones. So we have to think about what do sine functions look like. And then because when we start taking derivatives, we're going to need something about the cosine. And so let's look at the sine function. So this is our general shape of a sine curve, and we've seen it, and it just keeps going on and on forever that way, and on forever that way. And we usually have it in the area where we want to look, okay? So, maybe it's now this time we're actually putting things into radians, and before usually, we had different units. We didn't actually plot the sine curve versus the actual units for the open circle, or yeah, the open circle here. So what we're doing now is we're actually going to look at it as our unit circle. So, 0 degrees is the same thing as 0 radians. Then if we have pi over 2 radians, that's 90 degrees. And then 180 degrees is pi radians. And then 3 pi over 2 is equal to 270. And then we're back to 0. And this could also be considered 4 pi over 2, or just 2 pi. Okay, so that's our circle. And if we think about it, we can get this from our unit circle. And so what we would do is we're looking at its cosine comma sine. So the cosine of 330 is square root of 3 over 2. And then the sine of 330 degrees is negative 1/2. Or if we're using radians, same thing works. But if we notice here, at 0 degrees, or pi over 2 is 0, or not pi over 2, but the radians is 0, then we're at this point right here. Okay, and so it doesn't matter if we're on the sine or the cosine curve. We're going to go with both of them at the same time. So what happens is cosine of 0 radians is 1, and so 0 is 1. So we have that point there. But the sine at 0 is 0. So that's here. Okay. And then we just move our way through, and we can plot all these points along the way. And what happens is we get the nice sine curve here using the second part of the curve, the y part. And if we plot the x's, then we get this function. Okay, so pi over 2, which gives us 0 for cosine and 1 for sine. Well, that's 0 for cosine and 1 for sine. And as you can see, we're about pi over 2 units away from each other. So what we can do is we can say, well, the cosine function, f of x equals cosine of x, where x again is any real number, is related to the sine function through this notation. So cosine of x is equal to sine of x plus pi over 2. And again, that's this pi over 2 here, because what happened was the sine is basically, we're adding pi over 2 to it, and then that would get us from cosine to sine. Okay. All right. So again, knowing our unit circles again is going to be a key, but we could plot both of these off of the unit circle, so we can get both of these graphs from that unit circle. Now, what about the derivatives? Well, the derivatives we can come up with, we have our original sine function here and our original cosine function here. And what we can do is we can say, okay, well, let's go and make a slope graph. Okay, well, what happens there? Well, here we have a 0, and so that's that point. Here we have a 0, that's that point. Here again, we're going to have a 0, so that's that point. And now here we have going up, and that's our point of inflection. So that's going to be a max. Well, max on cosine or sine is 1, so that was going to be here. Now we're decreasing. Here's the point of inflection. That's going to be a minimum, and so that's going to be at the -1 at pi. And then it goes back up again and repeats. And so this sign goes over here to this. And well, since this actually looks exactly like this, what we say is, the derivative of f of x, or f prime of x, is equal to the derivative of x with respect to sine of x. That's equal to cosine of x. And so this and this are equal. So if we take the derivative of sine, we get cosine. Well, is that the same thing for cosine? So if we start with our cosine, well, here we have, that's going to be the inflection point right there. So that's going to be a max. So that's going to be up here. That's horizontal, so that's going to be a 0. And we come here, that's going to be decreasing, and it's on an inflection point, so that's going to be the minimum. Well, that's going to be at -1. And then here is going to be 0 again. And then we're going up, and that's an inflection point, and it's a positive slope, so that's going to be the max. And so we have that. And so that looks like our curve now. Well, if we look at that, that does not equal that, okay? But if we flipped this over the x-axis, it brought that down here, take that up here, take that up here, and these are going to be right there at that, and we draw that, that is going to be this. And so our derivative of cosine of x is going to be negative sine of x, because we're flipping it over our x-axis. So using the graphs, we're able to come up with our sine rule and cosine rule for change. And so if f of x is equal to sine of x, then f prime of x is equal to cosine of x. And if f of x is equal to cosine x, then f prime of x is equal to negative sine of x. Okay, so that's coming all again, from your trig that hopefully you've had, and so you understand the unit circle and how all that works there. All right, so up to this point, these are all the rules we've seen. So we've seen the constant rule. So if we have a constant, the derivative, that's equal to 0. The power rule, we bring our power down, and then subtract 1. So we have our derivative that way. B to the x, we take the ln of b times b to the x, and that's going to give us that one. And e to the x, if we took and used that e there, what happens is ln of e is 1, and so then we just have e to the x, and so that's how we get the e to the x rule. Now the natural log rule, if we have ln of x and x again is greater than 0, then it just becomes 1 over x, because we can't have 0 in our denominator. And sine, well, we found that was going to be cosine, and if we take the derivative of the cosine, it's negative sine. And then these are just some of the other kind of simple rules of constant multiplier. So we can have a number out front times a function, and then we just take k times the derivative of whatever the function was, and that's going to be our overall derivative. And we can add or subtract uh, functions, and then we just add or subtract their derivatives, and we get the derivative of the overall function. Okay. So those are the rules. And so up to this point, that's what you really need to have memorized to be able to do well on these first two sections as far as what are the derivatives. Okay, I'll stop there and I'll come back for more.